Hey, welcome back again. Here we go with yet another batch of learning for you. Can't even remember what we did. Oh yeah, isotopes and stuff, right? We learned about how there's all kinds of isotopes with the wave mechanical model, right? Because the wave mechanical model says we've got protons, neutrons, and electrons. Electrons, clouds on the outside in these things called orbitals. The nucleons, the protons, neutrons, they're in the middle, right? With protons and neutrons, protons, massive 1, neutrons, massive 1, protons plus 1, positive protons, neutral neutrons, right? You guys remember all that? Awesome. And then we started talking about isotopes, right? Where you can have one element, same number of protons, but you can have different number of neutrons all up in there. So, yeah, and when I mentioned that if you look at the periodic table of the elements, you will see that there's like actually lots of like weird averages in there, like 12.01 and 19 point blah blah blah. Like there's and you can't have partial proton or partial neutron. So what is that with the periodic table having all weird numbers for the atomic mass? Well, that's what we're going to look at today. We are going to look at how we calculate the average atomic mass that you find on the periodic table, because this is not your standard like average where you just like at like if you have 3, you count them up and divide by 3. That's a regular average. We are going to do what's called a weighted average, and that is how we find the average atomic mass. Here we go. All right, so the average atomic mass of that should be like of the element. So here's the deal. In any sample, excuse me, of an element, there is a fixed ratio of isotopes. And when I say fixed ratio, I mean it's like the same no matter what, a fixed ratio. So what that means is if we go to like Istanbul and we dig up iron, we'll find I'm making this up, we'll find 2 isotopes, this much of one, this much of the other. Now that's in Istanbul. Now let's go somewhere else. Let's go to County Cork in Ireland, and we dig up iron, and we find the same 2 elements, same 2 isotopes of iron, and we find this much of isotope A and this much of isotope B. That's silly. So what if we went to like, trying to think of another super random place. Oh, Tasmania. Speaking of like Tasmania, and we dug up iron in an iron mine, and we would have this much of the first isotope and this much of the second isotope. And where's another super random place like you can use iron? Oh yeah, what if we were like here, and we dug up iron from the mine? Guess what kind of ratio we would get? We would get this much of one isotope and this much of the other isotope. No matter, like, pretty much that's how it works. There are teeny little differences, but it really won't matter under normal circumstances, and you need some crazy equipment to like be able to slice that apart. And here's the reason why, is because, I mean, if you think back at how like the whole solar system was made, there's a big giant cloud of like galactic like dust from other stars exploding, and gravity started pulling these things together, right? And as the center, like they sort of started collecting together, and all these bits and pieces and fragments started like sticking together because of gravity, the gravity increased. And as the gravity increased, what starts to happen as things accelerate, they start to swirl and spin. I don't know if you've ever seen that. If you flush the toilet or watched water go down the drain, the water increases because gravity is pulling on it. So the water wants to accelerate, but it kind of can't. So what it does is it starts to spin. And that is what happened to the giant cloud that made up our solar system. And it didn't just spin and twirl and do that and like do its thing for like a day or two. We're talking like a cosmic amount of time. I don't know how much time, but like a majillions of years, okay? And then in the middle of this big giant ball of gas and whatnot, the pressure became so big that the sun ignited and blew everything kind of out. But that's not how the sun or how the Earth was made, because after the sun ignited, all the detritus was sort of blown out and away, but it still was starting to coalesce together. So it still started spinning around the sun and kept spinning, and things started colliding together and like making lumps, and that just spun and spun and spun until it formed a ball. But it wasn't just a solid ball, because it was a giant ball of molten like Earth, and that spun and churned and coiled and whatnot, until the outside layer finally cooled off and all the amazing things happened, and here we are today. Basically what I'm trying to get at is that the Earth was stirred up pretty good. It started out pretty much as a homogeneous mixture, all right? So it doesn't really matter where you go on Earth. If you like go into nature and extract like an element, you're going to have the same ratio of isotopes pretty much no matter where you go. because Earth. So that's why we get this fixed ratio of isotopes, and it works for everywhere. It doesn't matter what part of the world you're in, what country you are, it's all the same, okay? And so to figure this out, to find the average atomic mass of our elements, we need to use both the mass of the isotopes and this thing called abundance, right? And abundance, just like all it is, dude, it's just telling us how much. Does that make sense? It just tells us like how much. Like it's like percentage is really how we do it. So in our little example up here, this would be like 66% this and 33% that, right? So if this one, let's just say, if this one weighed 10, whoa, it's doing that thing again. So if this one weighed 10 and this one weighed 7, because there's twice as much of this stuff, we would expect the average to be closer to 10, right? And that's what I mean by like taking account like the abundance or like the amount, right? Or if we had a ratio that was like ooh, let's use a different color for a different ratio. If we had a ratio that was like this, where it was like 90% 20 and like 1% 19, we would expect, because there's so much more 20 when we put it on the scale, the average it was going to be way closer to 20 than it will to 19. You guys pick it up when I'm putting down? Awesome. That's what I mean by abundance and mass. Like how much does this stuff weigh and what's the ratio, right? Because if it's 99.99% isotope 12, it's going to be pretty close to 12. Do you know what I'm saying? So like for boron, the average atomic mass is 10.81. It doesn't mean that like it's 10 and 8/10 and 1/100th of a proton or neutron. It's like this is the weighted average, right? This is and by the way, a weighted average is how we do grades in this class. So it's not like it's new and weird or anything. It's how it is. So we know that the most common isotope for boron is probably 11. So any sample of boron, and the greatest ratio, or the isotope that has the greatest percentage, is probably going to weigh 11. And if you look at carbon, remember there was carbon 12, 13, 14? The vast majority of all the carbon atoms are really close to 12 because the average is 12.001, really close to 12. Same thing for nitrogen. Nitrogen is very, very close to 14. That is the most abundant isotope of nitrogen. And carbon, 15.99994, that's really, really close to 16 because the vast majority of oxygen atoms are the isotope oxygen 16. There are a few oxygen 15s, a very, very small amount. What is that like? I don't know. Very small amount. And so on and so on and so forth. But that's kind of how that average is figured out, right? And what we are going to do is figure out how to do it. Because math, why not, right? So, look, I'm going to talk at you, and then we'll do an example. Because the examples that's really how math is done, okay? We can talk about it. So, basically, to find the average atomic mass, and again, this is also a weighted average. To do that, first we take the percentage as expressed as a decimal. So what that means is like 98.2%, right? To make that into a decimal, you move the decimal place twice, it becomes 0.982. Are you guys with me on that one? A different percentage, if I may. If we had, let's do 23%. 23% even. Right? Well, if a percentage is a ratio times 100, we're just going to like undo the times 100. And so to make it a decimal, 23% turns into, very good, 0.23. All right, now are you guys ready for a more difficult one? I hope so, because I'm going to do this. Remember, we're going to move the decimal place over twice regardless, right? Because that's how the math goes. You have to move the decimal place over twice. So if you have something that's like 3%, you still need to move the decimal place over twice. So the decimal is here, and we're going to go 1, 2. So this will turn into 0.03. You dig? Because you got to move the decimal place over twice. Don't forget to do that. So, coming back here, the percentage expressed as a decimal is multiplied by the mass. Okay, so it's just percentage times mass. Okay, and then you take the product of all the, you do this for each isotope. For each isotope. Right? So you do this for each isotope, and then the products are all added together to get the total. That's your average. So let's look at a really quick example. Down here. Oh, hey, there it is. Okay, so here's the deal. This percentage, so here's an example of nitrogen and how we get nitrogen as 14.01. So this percentage has already been moved into a decimal. So now I'm going to ask you, what is the percentage for this one? Well, the percentage for that is going to be 99. Oh man, I just messed up. Hold on, give me a second. The percentage is going to be 99.63%. All right, because we're going to move that to make it a decimal. We move it over once, we move it over twice. Okay, that's how we get the decimal. Same exact thing for this one. The decimal is right here, right? So there's the decimal. I'm going to move it over twice to make it into a percentage now. Remember, up there, we were talking about percentage to decimal. Now we're doing decimal to percentage. It works both ways. So we're going to move it over twice. 1, 2. This is 0.37%. And before I go any further, let's try to predict what the average is going to be closer to. If 99.63% of your sample of nitrogen that you pull out of the air has a mass of 14, and only 0.37% has a mass of 15. It's less than 1%, man, is 15. Do we expect our average to be closer to 14 or 15? Well, dude, if it's 99.63, but it's going to be closer to 14, right? So here's the math. We take our percentage as a decimal, and we multiply it by the mass, and we get this thing called the product. We use a calculator, right? I do that for my first isotope. Then for my second isotope, I take the percentage expressed as a decimal, and I'm going to multiply it by the mass. In this case, 0.0037 times 15, using a calculator, because I can't do that in my brain. Then we get a number. Okay, so this is the product for 14, this is the product for 15, and then we just add those two together. And so what this is saying is that in our sample, the average 13.95 is from the stuff that weighs 15, and only 0.06, a very small amount, is coming from the stuff that weighs 15, which kind of makes sense because it's only 0.37%. I would not expect that to be a major player when it comes to like the average weight. You guys understand what I'm saying? Hope you do. If not, we're going to be doing this a lot to make sure that you can, because this is one of the few things that you cannot look up the equation for on the regions. So we need to commit this to memory. Also, this is kind of a thing we're going to be doing like all year. It's just a fundamental part of chemistry, being able to do like math like this. Got it? Sweet. Moving on. Oh, not moving on. Okay, I guess we're done. So that was super quick. What we're going to do for the worksheets for this are this one, average atomic mass, and when we're done, that one, that's like 4. Super quick. We'll do all those together, and then I'm going to let you loose on these ones. Average atomic mass worksheet. That one's spicy. But it's spicy for a reason, because I need you guys to be able to do this right out of your head without even thinking about it, okay? So, thanks for tuning in. Hold on tight for learning. Yeah, thanks again for, learning chemistry and being generally awesome people. I'll see you soon.